Good. I guess it's time to start. So great pleasure to have Mykola Matviichuk speaking today about Poisson brackets on projective bundles. Go ahead, please.
Okay, thanks, Akar. I would like to start by thanking the organizers for giving me a chance to speak here about these results. It's an honor. So I would like to start by by outlining some motivation for what I'm going to talk about. So consider this kind of dream problem. Suppose that if you are given a smooth projective variety over C, and suppose you could classify all the Poisson brackets. So the problem is to find such classifications for some concrete smooth projective varieties. Of course, in this generality, problem is stated is probably hopeless for most examples of varieties. However, there are several examples that have been solved. So first example that I want to mention is the fact that Poisson algebraic surfaces have been classified. So I think maybe the earliest paper I could find on this is by Bartocci and Macri. So they classified which algebraic surfaces admit Poisson structures, and they also, once you have concrete algebraic surface, you can calculate. It always has only one family of Poisson structures, and you can calculate its dimension. So that's what they did. Maybe a little bit more interesting example is the next one, is that of P3, so three-dimensional projective space. And here classification is turns out to be much more harder, of course, than for two-dimensional case. And actually, it's funny that people who solved this problem, they were not studying Poisson structures. They were studying this first two authors, Servan and Linsneto. They were studying certain holomorphic foliations, singular holomorphic foliations on projective spaces, and they proved some classification theorem for those foliations. And then later, Lorey, Pereira, and Touze noticed, and they explained how the results of the first two authors imply classification of Poisson structures on P3. So there are 6 families, and they describe all of them. And moreover, in the same paper, Lorey, Pereira, and Touze, they also pushed the classification for a certain family of Fano threefolds. Specifically, they classified Poisson structure for those threefolds whose Picard group has rank 1. And I mean usual classical Picard group, so the group of line bundles. So let me remind that there is complete classification of all Fano threefolds. So it's done by Mori and Mukai, and they listed something like, I think, 88 families of Fano threefolds, and they can also be all these families can be subdivided by the rank of the Picard group. And well, the simplest case, I think, would be to consider Picard group of rank 1, and there are, I think, 17 of them. So that's what Lorey, Pereira, and Touze did. They classified Poisson structure on these 17 families of Fano threefolds.
Can I ask a question?
Yeah.
This set of holomorphic Poisson structures, is that in some sort of variety, or can one say anything?
Well, in general, it's if you just consider all Poisson structures that it's a variety, it's cut out by the integrability equation. Pi bracket pi is equal to 0. It's usually algebraic equation on algebraic varieties. However, typically you would also want to mod out by the automorphisms, and then it becomes a pretty bad space. It's a stack, and it's kind of all kind of weird phenomena can show up in the stack. It's not, I don't think it's still in Mumford stack. It's usually pretty bad space. Yeah. Mm-hmm. Okay. So a little bit further, a classification of Fano threefolds, of Poisson Fano threefolds, was also done for several Fano threefolds who have Picard rank greater than 1 by Bellmans, Fatigenti, and Tanturi. But their classification is kind of, in a sense, it's trivial. So they calculated the global bivectors, and they found several Fano threefolds where there are no global bivectors at all. So the calculation itself is, of course, far from trivial, but the end result is kind of trivial. There are no Poisson structures except the 0, 1. So in this way, it's a classification. And I suppose, of course, that you can come up with many more manifolds of this type when there are just no global bivectors. So in this case, of course, you obtain classification, but it's maybe not so interesting for Poisson geometers. Okay, and so these are pretty much all the results that I know about the problem that formulated in this way. There are similar results about Poisson classification of Poisson varieties, which stated a little bit differently. So there is also a result of Druel. He explained, he classified Poisson threefolds that have the condition that the Poisson tensor vanishes only at a finite number of points. So it doesn't vanish on a curve, it only vanishes at isolated points. So he classified all those projective threefolds, and he has description of them. And maybe I should also mention a result of Verbitsky, who was studying moduli space of holomorphic symplectic structures that are deformations of given hyperkähler manifold. So he gave a description of this moduli space. I think it's still not quite a classification, but it's some kind of nice result about this moduli space. I'm not sure if that can be considered a classification, but still a result worth mentioning in this context. So apart from this, I think that's pretty much all the results about classification of Poisson varieties that I can think of. And today I wanted to talk about 2 more examples where this classification of Poisson structures can be done. So the first of the 2 cases is going to be the main object of today's talk. It's going to be P2 bundles over P1. So I can classify the Poisson structures on P2 bundles over P1 under some mild condition, which I'll clarify later. It's kind of technical assumption, but it is an assumption that I'll have to impose, and it prevents me from saying that I can classify all Poisson P2 bundles of P1. So I'll explain what this mild assumption is later. And then the last case is a classification of log symplectic brackets on P4, and the additional condition that these Poisson brackets admit toric degenerations. So this last one is joint work with Pim and Chandler, and actually Brent already gave a talk about this classification on this very seminar. So I'll describe it a little bit, but if you want more details, and if you're interested and you want to know more about it, then I encourage you to go into Nikita's website and find this recording of this talk. Okay, so that's about all I wanted to say about motivation. And let me now start by discussing the last case first, and then I'll switch to projective bundles, unless there are questions. Okay, so let's talk about log symplectic brackets on P4. So I want to start with a simple kind of log symplectic brackets, precisely with the ones that are given, that are invariant under the action of the 4-dimensional torus on P4. So I want them to be generically symplectic, and so I can invert and obtain a 2-form, and this 2-form has to be of this form. It has to be this very simple form, where Bij are certain constants and x's are homogeneous coordinates. And so if you choose constants Bij so that they form a matrix of full rank, then this form gonna be symplectic. However, it will have poles necessarily, and in this case, the poles are gonna be over the 5 coordinate hyperplanes, and they are gonna be the simplest kinds of poles. They of order 1, moreover, they're logarithmic poles, meaning that d of a pole is the form has logarithmic pole if it has first order pole and differential, and d of it also has first order pole. So omega has logarithmic poles along these 5 hyperplanes, and now I want to start with this simple Poisson bracket and deform it. And of course, Poisson bracket does not have a poles. It's only the form that has poles, but Poisson bracket is nice holomorphic, smooth everywhere. So if you study deformation problem for such Poisson structures, then you notice you can pretty quickly figure out that if you choose constants Bij sufficiently generically, then the only way to deform such a Poisson bracket would be to deform the constants, and that's it. You cannot construct any other deformations except the obvious ones. However, what we do in this project with Brent and Travis, we explain that if these constants are chosen just right, then you start getting more interesting deformations of this Poisson bracket. And the deformations are no longer preserving the structure of the divisor, they also move the divisor. They the divisor starts kind of, some components of the divisor start merging together and form, so before they were just hyperplanes, pretty simple, but after they merge, they form some more interesting components with more complicated singularities than just normal crossings. So what we do in that project with Brent and Travis, we described all such ways to deform this log symplectic form. And the answer we phrase is purely in terms of the de Rham cohomology class of omega in the complement of the divisor. Well, I guess for this case, it's not at all surprising that the answer should depend only on this de Rham cohomology class, just because the constants are precisely, the constants Bij precisely encode the same information and this de Rham cohomology class. However, what's a little bit surprising that this phenomenon is true for, in much more bigger generality, it's true for any log symplectic structures whose divisor has normal crossing. So we prove that deformations of such log symplectic structures, they purely encoded in terms of the topological data given by the 2 form, even though what we are deforming is actually a holomorphic object. So this way we describe all the deformations of toric Poisson structures of full rank, and this way obtain this classification. And we find 40 families of such brackets. And let me talk a little bit about the tools that are used in this classification. So first of all, we need to calculate deformation complex, and deformation complex for Poisson brackets is the Poisson cohomology. So that's the first important step that we have to do. And to be honest with you, it was kind of a surprise, another surprise about this project, that it turns out you can calculate Poisson cohomology pretty explicitly for pretty much all examples. We didn't expect that, but yeah, it can be done. The Poisson cohomology can be calculated quite explicitly for log symplectic structures with a normal crossing divisor. And the second step is, once you calculate the Poisson cohomology, now by taking Poisson bracket on polyvectors and applying homotopy transfer, you obtain all this family of L-infinity brackets on the Poisson cohomology, and you have to find a way to control them. And well, we cannot calculate all L-infinity brackets very explicitly, but we kind of develop some description for them that is good enough to be able to solve the deformation problem, to solve the Maurer-Cartan equation for this L-infinity algebras. Okay, so that's kind of overview, that's the extent that I wanted to talk about this project. Yeah, if you're interested, please go ahead and watch Brent's talk. And we also have preprint about it. Okay, so unless there is a question, let's see what the question is. Are there infinitely many non-zero brackets? Yes, in general, yes, infinitely many. Yeah, there are infinitely many. I think we can also probably construct example where we can show that you cannot get rid of all brackets of higher arity. Then how does one interpret MC equation? Oh, MC equation, when you have infinitely many brackets, then it's like when suppose gamma encodes the deformation, then you kind of, so the usual MC equation is like this. Let me move a little bit because it obscures. And then you have the higher order terms, and they always of the form 1 over n factorial, and here you put bracket of arity n. And so on. And so here would be 1 over 4 factorial bracket of arity 4 applied to gamma 4 times. And I guess you're asking about the convergence, or does this answer the question, or are you asking about the convergence? So this is MC equation for infinity brackets. Okay, so the convergence, we handle using Artin approximation theorem. So, so what we actually do with this, describe the moduli space, formal neighborhood of in the moduli space. But then if you are on a compact manifold, then it's actually the space, it's actually the integrability equation is finite dimensional, because the global set of the set of global bivectors is finite dimensional, and integrability equation imposes finitely many equation on the bivector. So there is general theorem of Artin that tells that if you describe the formal neighborhood in the moduli space, then you actually obtain description of the analytic neighborhood in the moduli space. So we kind of postpone the convergence issue till the very end, and then we use Artin approximation theorem to deal with it. Okay, thanks for the question. Okay, any more questions about this before I move on to the next topic? Okay, so now let's talk about Poisson brackets and projective bundles. So in the end, I want to concentrate on P2 bundles over P1. However, let me start with a general setup. The only condition that I want from the projective bundle that it is a projectivization of some vector bundle, holomorphic vector bundle. So for the over the curve, if X is a curve, this is automatic, but otherwise it's a condition that I'm assuming. So let's write down the expression for the for any Poisson tensor on such space. So it will typically have 3 terms. One of the terms will be kind of involve two horizontal components, then there will be terms that has one horizontal, one vertical component, and then there will be completely vertical term. And by vertical, I mean tangent to the fibers. And now let's assume furthermore from that this Poisson tensor satisfies the condition that the fibers of the bundle are coisotropic. So in coordinates, it just means that the first term is 0. Then the next term, the second term, actually forms a well-defined tensor over the base. It's tensor of the form T of X, tensor product with endomorphisms of V. And T of X here stands for tangent bundle. And this tensor is well defined, and it satisfies, so that it satisfies this condition, which follows from the Poisson integrability condition for sigma. You can check that integrability of sigma implies this condition for phi. And such tensor that some tensor of this form that satisfies this condition is called co-Higgs field. So it's very similar in nature to the Higgs field introduced by Hitchin. And co-Higgs fields, modular space of Higgs fields has been an area of active research ever since Hitchin introduced them. So Higgs fields are just the same type of object, but you replace tangent bundle with cotangent bundle. So as I said, modular space of Higgs bundles, meaning vector bundles with Higgs field on them. The modular space of Higgs bundles is very well studied, and it has holomorphic symplectic structure. It has a lot of structure. So modular space of co-Higgs bundles is not as well studied, but nevertheless, Steve Ryan has a PhD thesis where he describes that this modular space is still possesses quite a lot of interesting structure, and it's an interesting object to study. The other way that co-Higgs fields are important is in generalized geometry. So in generalized complex geometry developed by Hitchin and Gualtieri, co-Higgs bundles serve as generalized complex bundles over ordinary complex manifolds. Yet another way why co-Higgs fields are co-Higgs bundles are important is because when you consider Poisson's manifold with 0 Poisson structure, then co-Higgs bundle over such manifold is precisely a Poisson module over 0 Poisson structure. So yeah, there are several ways how co-Higgs fields are important in Poisson geometry and generalized complex geometry. And so I hope to convince you today that there is yet another way how they are important, is because they can help you study Poisson structures on projective bundles. Okay, so what I'm gonna do in this talk is to study how having a concrete co-Higgs field to find whether it corresponds to some Poisson structure in this way. But before doing that, let me also give alternative definition. So I gave the definition in coordinates, but let me also give coordinate-free definition of the co-Higgs field. So I need to use the canonical correspondence between vertical vector fields on the projective bundle and zero trace endomorphisms of this vector bundle. So this is just a relative version of the classical correspondence between vector fields on projective space and zero trace matrices. And you can obtain the Higgs field out of the Poisson tensor this way. So you think of co-Higgs field as a bundle map from T star to N0 of V. So N0 of V is traceless endomorphisms. And this bundle map is described the following way. You take one form, locally defined one form on the base, you pull it back to the total space of the projective bundle, and you consider a Hamiltonian vector field of this one form. So because we assume that the fibers are coisotropic, this vector field has to be tangent to the fibers. And so you can recast it as endomorphism of this vector bundle using the correspondence above. So that's a coordinate-free description of phi. Now let's start discussing this connection between co-Higgs bundles and Poisson projective bundles. But before doing that, I would like to overview the classical spectral correspondence introduced by Bouville, Narasimhan, and Ramanand for curves, and by Simpson for varieties of higher dimension. So this is a nice geometric way of encoding information about this tensor phi by recording its eigenvalues and eigenvectors. So here I'm thinking of phi as a matrix whose entries are vector fields. So just as for any other matrix, you can consider its characteristic polynomial, except in this case, characteristic polynomial has coefficients which are sections of the symmetric powers of tangent bundle. And this characteristic polynomial can be interpreted as a section of some vector bundle on Tx. And you can consider the zero set of that section. That's called spectral variety. And it's called spectral variety for this very simple reason, because it encodes over each fiber, it encodes precisely the eigenvalues of this matrix, T. And now the spectral correspondence also tells you that there is a way to encode eigenvectors as well, not just eigenvalues. And that's encoded by some kind of sheaf that is supported on this spectral variety. So this is one-to-one correspondence, and as I said, so sigma encodes eigenvalues of phi, while the sheaf supported on the sigma encodes the eigenvectors. And to obtain the co-Higgs bundle back, you just need to push forward this sheaf to the base to obtain some higher rank sheaf or vector bundle. So let's think of a vector bundle case. You push forward the sheaf, you obtain vector bundle in the base, and then the co-Higgs field itself is just multiplication by some topological section on Tx, on the pullback of Tx to itself. Okay, so as I said, this is quite nice and geometric, because instead of writing down some matrices with vector field values, we can just try to come up with varieties and sheaves on them, to construct co-Higgs fields. Okay, so let me start now. Let me come back to the question about co-Higgs fields versus Poisson structures on the projectivization. So it turns out that this notion seems to be important for as long as you want to consider Poisson geometry here. So let me further call a co-Higgs field strongly integrable if the coefficient of its characteristic polynomial pairwise Poisson commute when they viewed as functions over cotangent bundle. Tangent bundle has natural Poisson structure, so you can take Poisson bracket of this coefficients, and I want them to all Poisson commute. Equivalently, if you happen to be able to diagonalize co-Higgs field, somewhere locally, then this condition of strong integrability is just the same as requiring that the diagonal entries Lie commute. Entries are vector fields, and I want them to Lie commute. Then the co-Higgs field is called strongly integrable. So note that this condition does not exist for Higgs fields. It's somehow important that we are doing co-Higgs fields, because for Higgs fields, those coefficients Si, they would be sections of symmetric powers of T star, and there is no bracket. There is no Poisson bracket for such things. Anyway, so here's why this definition is important, why this notion is important. Turns out that as long as the co-Higgs field has reduced spectral variety, well, that's an assumption, but as long as it has a reduced spectral variety, then if you have a hope of finding Poisson structures that generate this co-Higgs field, then you must assume that co-Higgs field is strongly integrable. So that's a necessary condition for finding Poisson structures out of this co-Higgs field. Okay, this is necessary condition. It's far from sufficient, but let's just remember that it's necessary condition. And let's let me present another necessary condition. So recall there is a result of Poisson about lifting a co-Higgs field to a Poisson structure in the case of a rank 2 vector bundle. So Poisson proved that if you have rank 2 vector bundle, then any zero trace co-Higgs field on this vector bundle produces uniquely a Poisson structure on the P1 bundle that is projectivization. So kind of you don't have to worry about anything else. You don't have to worry about any conditions here. You always have Poisson structure.
Mykola, just a question.
Yeah, sure.
So since you are using strongly integrable, presumably there is some concept of integrable. What is an integrable co-fields?
Oh yeah, sorry. Yeah. Thanks for the question. I forgot to say that in the definition of the co-Higgs field, this condition is called integrability condition.
Oh,
so
okay. All right, thanks.
Yeah, I forgot to say that. This is integrability condition, and strong integrability, you have to assume this. On top of that, you assume that this coefficients Poisson commute. So actually, you need to assume integrability to define these coefficients, otherwise they are not really well defined. And then you have to assume that they Poisson commute. Okay, and so I said here that strong integrability is necessary, but then I didn't mention it in Poisson result, just because for rank 2 co-Higgs field, there are only 2 coefficients of the characteristic polynomial, and here he assumed that one of them is already 0, so there is no condition to check here. It's interesting that integrability is 0 order. Sorry, what do you mean by 0 order? Yes, I'm a little bit confused. Oh yeah, I see what you mean. I see. Yeah, so it doesn't involve any derivatives. Yeah, it kind of involves this integrability condition for co-Higgs fields. I could have, it doesn't matter if I put product here or the bracket, because the product is skew symmetric in this case. So I could put Lie bracket here, meaning that you take commutator of 2 matrices, but whenever you multiply 2 entries, then you multiply, then you take wedge of them. And then in that case, you have Lie bracket, which is kind of like Lie bracket of vector fields, except in this case, vector fields are linear. So yeah, there is no derivative for that reason. But in principle, yeah, you can think of it as some kind of differential equation if you want. Okay, so for rank 2 vector bundles, there is no condition. You always have a Poisson structure. However, in the contrast to that, another, okay, Brent is answering some question. Okay. In the contrast to Polyshuk's theorem, turns out that when you take, I just consider the simplest case when you have the base is one-dimensional, and whenever the rank of the vector bundle is greater than 2, it turns out that there is another important constraint on the co-Higgs field, that its spectral curve cannot be smooth as long as it has at least one branch point or ramification point over the base. So as long as it has at least one ramification point, it cannot be smooth. So for instance, if you want to consider spectral curve, something like this, you're not going to be able to find any Poisson structures out of it. Or in more complicated example, when you have y to the power r is equal to x, so r to 1 branched cover in such a way that the curve is smooth, and this projects onto x variable. So this is r to 1 branched cover. It turns out that you cannot, no matter what shift you put on such a spectral curve, the corresponding co-Higgs field will not have a Poisson structure. Poisson structure will have to blow up along the central fiber. We'll have to have a pole. So the moral of this story is that if you want to construct some interesting examples out of co-Higgs fields, you have to start considering the case when the spectral curve is singular. So smooth spectral curves are not good enough for this purpose. Maybe they're too good. We have to start considering a little bit less and worse behaved curves. Okay. So from now on, so far everything I said was in general, so it was general type of results, except that for this last theorem I assumed that the base has dimension 1. Now, moreover, I want to specialize to the case of projective P2 bundles over P1. And they always come as projectivization of some rank 3 vector bundle over P1. So let's fix a Poisson. Let's assume we have a Poisson structure on such P2 bundle, and let's consider its co-Higgs field and its spectral curve sigma. And the standing assumption that I'll assume throughout the rest of the talk is that this curve is reduced. So I don't want like double curves or triple curves. I want just like reduced curve with no multiplicity. So that's the mild assumption that I'm assuming. I think it's mild, but so that's the assumption that I'm assuming throughout the rest of the talk. And the first question one can ask, now that we know that smooth curves are not going to produce us any Poisson structures, we want maybe to look at singular curves and try to classify what kind of singularities these curves can possibly have. It turns out there are not that many of them. If you go and try to classify all the singularities that you can obtain, there are only 4 types of singularities. So there is A1, which is just intersection of 2 lines. There is D4, which is intersection of 3 lines in a plane. Then there is E7, which is intersection of a cuspidal curve with a line in such a way that the line is tangent to the cusp. And the last one is 3 parabolas tangent to each other in one point. So these names A1, D4, E7, T36, they may look a little strange, but it's the standard names from the Arnold classification of singularities. So I just use them because they kind of solidified. It's like usually the notation people use for this singularity, for this curve singularities. So there are only 4 singularities. And so that kind of gives a lot of constraint on the possible singular curves, on the possible spectral curves, sorry, for the co-Higgs field. So using this result, I will try to discuss classification of Poisson P2 bundles over P1 in the following strategy. So for each of these 4 singularities, I want to classify local normal forms for the co-Higgs field. If I manage to do that, then I want to, for each of these local normal forms, I want to check whether they produce any Poisson structures. So like, I remember that, for instance, smooth curves don't produce any Poisson structures. So I want to also to check and to ask the same question for each of the local normal forms here and check whether they produce any Poisson tensor on the P2 bundle over small disk or unit disk. And then if I manage to do that, I want to discuss all the ways to glue this local P2 bundles over small disk together to form a global Poisson P2 bundle over P1. And that's a kind of general strategy, which I want to discuss now. So, let's see the question. Can you say in a couple of words why you get precisely this for singularities? Okay, so first, you from the previous results, you know that sigma has to be strongly integrable, so that oh, even before that, so sigma is has to be cut out by equation, by characteristic equation of this form f of xy is equal to 0. And well, when y, I think of y as a coordinate on the tangent fibers and x is coordinate on the base. So because we're talking about rank 3 vector bundles, so the degree of y in this equation has to be 3, and degree of x has to be at most 6. And this is because the biggest coefficient in the characteristic polynomial is section of S3 of the tangent bundle, and this is 06 on P1. This is 06. Oops, 06. So the degree of x is at most 6 and degree of y is 3. So that already gives you some bound on all possible singularities. And when you do that, when you classify all possible singularities for this type of equation, you get bigger list. Then you have to cut down that list using strong integrability condition. And then moreover, so after that, you obtain something like 7 singularities. And then you manually check that 3 of them somehow don't produce any Poisson structures. And so that's kind of like you're kind of cutting down possibility step by step, first by just considering this equation abstractly, and then using strong integrability, and then finally remembering that there should be some Poisson structure corresponding to it. Yeah, thanks for the question. So let me start by describing now this strategy. So let me start with the first question. What are the local normal forms for the co-Higgs fields? So let me think of small disk or formal disk, and I have some vector bundle over this disk, necessarily trivial. It has to be trivial vector bundle, and I have co-Higgs field on this vector bundle. And let's assume we fix a spectral curve, like in the previous picture, we have 4 possibilities for the spectral curve, essentially. Yeah, 4 possibilities for the spectral curves, and we're asking what kind of co-Higgs fields and have the spectral curve. Well, for instance, if the curve is smooth, which is not our case, but suppose if we had a smooth curve, then it's well known that all co-Higgs fields are isomorphic to each other. And by the way, since we're doing locally, co-Higgs field is the same as Higgs field in this case. There is no distinction. So you can say all Higgs fields are isomorphic to each other, and so in particular isomorphic to this one. And one can ask, is there some result like that for singular curves? Well, so the spectral correspondence gives you a reformulation of this problem. It tells you that isomorphism classes of co-Higgs fields with given spectral curve in one-to-one correspondence with isomorphism classes of torsion-free rank 1 sheaves over curves, or this fixed curve sigma. And well, it turns out that this torsion-free rank sheaves were classified for several simple types of singularities. So there is ADE families of singularities. There are TPQs family, which are a little bit more complicated than ADE, but still in some sense tame. And a couple more. And these results are considered well known in the literature of Cohen-Macaulay modules, but somehow they're not considered well known in the, as far as I mean, I asked around, and I think people in Higgs bundles community don't, like these results are not considered well known in that literature, in that community, which is a little bit surprising, but, and of course, these results are not really well known in Poisson community. as far as I understand. So I'm trying to popularize this approach. So Cohen-Macaulay modules means, so there is algebraic definition. However, if you're talking about one-dimensional curves, then Cohen-Macaulay module means just torsion-free sheaf. And using this classification available in this literature called Cohen-Macaulay modules and spectral correspondence, I worked out several singularities and produced several local normal forms. I described all local normal forms for several singularities, in particular for the ones that I mentioned in the previous page. So in A1 case, I obtained two possibilities, two isomorphism classes. In D4 case, 7. In E7 case, 8 possibilities. And the last one gets a lot of possibilities. It's 21 possibilities plus infinitely many isomorphism classes parameterized by one continuous parameter. So for instance, let's consider the case of D4. Yeah, so for A1, the possibilities are quite easy. And this case is actually very well known in Higgs bundles community. That's two sheaves on such a curve correspond either to the trivial sheaf or to the ideal sheaf of a point. There are two possibilities for torsion-free rank 1 sheaf for A1 singularity. But for D4 singularity, there are many more possibilities. So let me just briefly discuss them, like what they look like. In fact, I can even draw a picture to kind of encode them. So there are 7 possibilities in this case, as I said, and you can draw a picture to each of them, signifying the following. So the singularity itself looks like this. It's just 3 lines in a plane. But then you can produce all kind of partial normalizations or partial desingularization of such singularity. You can either take one of the lines apart, or you can take all 3 of them apart, or finally, there is this more sophisticated way to desingularize such singularities, to push one of the lines kind of orthogonally to the plane containing the other two. And you obtain different singularity this way. And so what you should do is to take a structure sheaf of this partial desingularization and push it forward on the original singularity, and you obtain some kind of torsion-free rank 1 sheaf, and that corresponds to co-Higgs field. Except that in the last case, you can take structure sheaf like trivial line bundle, but also you can take dualizing sheaf. Every curve singularity has trivial sheaf and dualizing sheaf, except that in a lot of cases they coincide. Here they don't coincide, so you obtain 2 different possibilities in this case for the torsion-free rank 1 sheaf. And okay, so yeah, you can draw a similar picture for other cases. So let me summarize that we have this number of local normal forms for each of the 4 singularities that are relevant in this case. Now we want to start answering the second question. Now that we all these co-Higgs fields, which of them actually produce some kind of Poisson structure on the projectivization of a vector bundle? And it turns out that there is another important. There is important 2 cases that you have to consider separately. So if you have a strongly integrable zero-trace co-Higgs field on a rank 3 vector bundle over P1, that's kind of what we're dealing with. And you can call it either resonant or non-resonant, depending on the following. So if it contains the 0 section of the tangent bundle, then you call it resonant. If it doesn't contain the 0 section, you call it non-resonant. Okay, so this definition might look a little strange. So why would you exactly assume? Why would containing 0 section makes such a big difference? And the answer is given by the following proposition. So if you are in a resonant case, then it turns out that all these local normal forms that I listed here they all produce they all produce a Poisson structure, which necessarily have to be different. So they all produce some kind of Poisson structure on P2 bundle over small disk, small one-dimensional disk. However, if you are non-resonant case, then first of all, some singularities are not permitted. So A1 and E7 are out of the game in this case. And moreover, for D4 and T36, and not all local normal forms for the co-Higgs field are allowed. And well, I don't really have good understanding for which cases are allowed, which don't, but at least I can list all of them. I can list all the cases that produce some Poisson structures within these ones. So the moral is that in the resonant case, you have more flexibility for constructing Poisson structure, and in a non-resonant case, you somehow are more constrained. Okay. So that kind of answers the second step, which is what kind of local Poisson structures we can obtain from co-Higgs fields. Well, let me give an example. Maybe it sounds a little bit abstract, could look a little bit weird, but let me give some concrete examples. So this is the case when spectral curve has A1 singularity, so which is just transverse intersection of two curves. So let me also maybe draw them in appropriate color to match the picture. Sorry, I cannot get rid of this. Okay, so let me draw spectral curve like this. So there is a red branch and there is also green branch, which is just the zero section. So that's the spectral curve inside the tangent bundle of P1. And then, so you could construct co-Higgs field out of it. And it turns out it produces Poisson structure on the projectivization of n3 vector bundle. And Poisson structure has the following picture. So the eigenvalues of the co-Higgs field are depicted here in kind of appropriate color. So the parabola in the horizontal plane corresponds to eigenvectors corresponding to these eigenvalues given by parabola here, while this transverse line corresponds to eigenvectors corresponding to the zero section branch of the spectral curve. And there are this in each fiber there is a nice family of quadrics. It's pencil of quadrics which are given by the integral line of this vertical vector field given by this matrix. This matrix gives you vertical vector field in each fiber up to a constant, and you can draw integral lines, you know, how you call them, trajectories of this vector field. So they form a pencil of quadrics in each fiber. And this family of quadrics is completely determined by the co-Higgs field itself. You don't need to know the full Poisson structure to draw them, but what Poisson structure does, it kind of finds a way to identify the nearby family of quadrics. So it kind of produces data of Poisson structure. Once you fix this co-Higgs field, is equivalent to some sort of connection on the family of quadrics from fiber to fiber, which varies from fiber to fiber. So the resonant case is nice in this way, is that you can draw some nice family of quadrics in each fiber. It's always going to be, even for more complicated singularities, which there are a lot of possibilities for in this case, you can always draw these families of quadrics, and they're going to have some degeneration over the central fiber, and this degeneration is going to be different for different cases. Okay, maybe let me skip non-resonant case because it's kind of, sorry. Let me skip describing non-resonant case to save time, and let me just concentrate on stating the final statement. It's going to be a little bit long, but you know, it's a classification result, so supposed to be long. Anyway, the classification result will be about Poisson structure and projective bundles, projective P2 bundles over P1. And standing assumption is that I assume the spectral curve of the corresponding co-Higgs field is reduced. So the statement that all such Poisson structures can be obtained in the following way. So let me start by repeating the steps that we already discussed. So first, you have to fix a spectral curve. It has to be strongly integrable and has to have only one of these 4 singularities. Moreover, you can say how many singularities, what combinations of singularities are allowed. You can assign weights to each of these singularities, like 1, 2, 3, 4. And then the rule is the total number of the total sum of weights has to be exactly 4. So it's kind of you may have 1 T3-4 singularity, or maybe you have 2A1 singularity plus D4 singularity. So you have all these possible combinations for the singularities for the spectral curve. Then after that, after you fix spectral curve, satisfying these rules, near each of the singularity, you have to choose local normal form from the list that we discussed. And the rule is that if your spectral curve was resonant in the first step, then you have no restriction. You can choose any local normal forms for the co-Higgs field you like. However, if the spectral curve is non-resonant, then you have some constraints. So you cannot choose all possible local normal forms. You have to be you have to choose only the ones that are allowed. In the third step, we have to choose a spectral sheaf on the spectral curve. And well, since we already specified the local behavior near each singularity, the spectral sheaf has specified behavior near each singularity of sigma, but there is still some more freedom in how we choose it globally, the spectral sheaf on sigma. And it has to satisfy a further global condition, which is very specific condition, but I cannot state it because it depends. I cannot state it during the talk because it depends on considering cases. So it's kind of several conditions depending on each case. So I'll discuss it a little bit for one of the cases in a minute. What kind of condition is that? But after you've done that, if you chose all this data and you were following all the rules that I was talking about, then using true spectral correspondence, you automatically obtain a co-Higgs field, and it's guaranteed that this co-Higgs field has a Poisson structure associated to it. And the claim is that all the Poisson structures are obtained this way. Okay, so just a couple of words. I really like this global condition is essentially the only new ingredient in this theorem compared to the previous slides. And I didn't say much about it, so let me give an example. So this global condition, as I said, will depend on the case you're in. And so not only resonant case is different from non-resonant, but also each of these cases has a few subcases, and in each subcase, the condition is going to look a little bit different each time. So that's why I kind of didn't want to state all the 6 conditions, but let me state one just to give a feeling for what kind of condition that usually is. So for instance, in the case when we have resonant co-Higgs field and assume that co-Higgs field never vanishes completely. So this matrix always has non-zero entry over each point. Then the condition has to be like this. So this is if and only if condition in this case for existence of the Poisson structure. Here D1 is the degree of the sheaf on the 0 section, and then maybe the curve could have 2 other components and maybe one another component, depending on what kind of curve it is. So the D23 is either the sum of the degrees on 2 other components or the degree on the remaining component. So the case when there are 3 components could be like this, for instance. This is the case when there are 3 components in the spectral curve. But I won't resonant case, sorry. This is another case which is allowed. And M here, this number M, it has geometric interpretation, but more importantly, it's very computable number that you can just look at the spectral data and calculate. And this number M, moreover, has local nature. So once you have specified local behavior in step 2, you already know what the number M is. And then the third condition is really about choosing the degrees of this sheaf in such a way that they satisfy this equation. So it could be equation on degrees. Sometimes in other cases, it could be some inequalities on the degrees. And it's kind of conditions like that in each case that are if and only if conditions that provide you Poisson structure in the end. So yeah, so that theorem kind of classifies all the Poisson structure in this combinatorial / geometric way. And I think it's a good place to stop. So thanks for listening.
Yeah, thanks a lot, Mykola. So do we have questions? Okay, Anton has a question.
Yeah, I've got a very naive question, which probably refers more to the beginning of the talk. So one of your ideas or one of your requirements is that the coefficients of the characteristic polynomial, they Poisson commute, right?
Yeah.
So this means this is a sort of integrable system, and of course, in the Higgs field case, those Hitchin integrable systems, kind of they are well studied, they're famous.
Kind of frozen.
Integrable systems, like from the integrable system point of view, what are those commutabilities? Can one imagine? I don't know whether you hear me because my machine says that my connection is unstable.
Yeah, if you could repeat the last sentence.
So what's the integrability angle? Can kind of what can one say about those systems as integrable systems? Do we recognize some famous examples in some simple cases?
Right. Yeah. Yeah, I think so. There is this nice case in like when the base has higher dimension. So most of my talk was about the one-dimensional base, but there are some examples in higher dimensions where why you would need higher dimensions, because if you have say R functions that you kind of want the variety to have dimension two times R. So you would want the base to have dimension R as well. And the examples where this kind of forms integrable system on T star of X. This would like if dimension of X is equal to the rank of V, then these R coefficients will be exactly have exact number which will exactly have how should I say, sorry, the dimension of this is 2 times D, where D is dimension of the base. So you would need R to be equal D. So you would need the rank of the vector bundle to be equal to the dimension of the base manifold for this to be integrable system. And the examples of this type are the following. So you can consider a curve, and you can consider a symmetric power of the curve. And you consider kind of like, you think of this as modular space of D points on the curve, and then you consider universal, kind of universal modular space, which means that over each fiber here, you place precisely these D points of the curve that this fiber represents. And what you can do with this picture is you can take any line bundle here on C, and you can push to this universal moduli curve or universal moduli space. And then after you push it on the base, you obtain a rank D vector bundle. And you can construct examples like this. And in that case, there is nice co-Higgs fields, co-Higgs field associated to this picture. And you would obtain an integrable system in that case. I guess I'm not quite sure whether it relates to any classical integrable systems.
Okay, thank you.
But it's an example, yeah.
Yeah, other questions?
Can I ask you one question?
Yeah, please go ahead.
So this condition that the spectral curve is reduced, can it be easily translated for the original holomorphic Poisson structure having some property?
Right.
Because you are classifying a subset of holomorphic Poisson structure.
Yeah. Yeah. Right. Yeah, I guess that's. I guess I'm not sure how. I'm not sure if there is a nice answer to that. Okay, I guess the one way to answer is that the Hamiltonian vector fields of the functions that are pulled back from the base. The condition is the Hamiltonian vector fields of the functions that are pulled back from the base do not have double zeros. They only have like 3 separate zeros in each fiber.
Is that like a condition that is implied, or is it equivalent, or you think it's equivalent?
I think it's equivalent to requiring that the spectral curve is reduced. Maybe I think it's like that. And then Brent says, does it correspond to the locus, to the zero locus of the Poisson structure being reduced? Yeah, I guess I'm not sure about this question. Whether the answer is yes. I mean, Brent's question.
The other question I had is it easy? I mean, these holomorphic Poisson structures, they are going to be integrable in terms of they're going to integrate to holomorphic symplectic groupoid, if I understand.
Oh yeah, yeah. I guess that's a very good question.
It's about the local models that you have. Maybe if you think in terms of the corresponding locals models for the corresponding holomorphic symplectic groupoids, they are easy to get.
Right. Yeah. No. I've been keeping this question in mind. I don't have anything smart to say, but I agree that it looks like it's would be very interesting if we could construct symplectic groupoids of the local models and then start gluing them together. Yeah, that's it's a very good point. Yeah.
Thank you.
There's also a question in the chat from Dima Reutenberg.
Okay.
Where do the Poisson cohomology and L infinity bracket calculations come into the story?
Yeah, so that part was kind of localized to the project on P4 bundles. So that's just separate project, and the methods for two projects are kind of very different. So L infinity brackets and Poisson cohomology, that was needed for the classification of Poisson brackets on P4. And for projective bundles, yeah, I don't explicitly use L-infinity algebras anywhere. And I mean, yeah. Unless I should interpret your question as question about the deformations of P4 brackets. Then, yeah, I guess if your question was about deformations of brackets on the P4, then I don't really, yeah, I don't have a good answer. It's just infinity brackets on.
Yeah, no, it's just you mentioned that at the beginning of the talk, and by now I had forgotten which part of the project that was referring to. So
okay.
That answers my question. Of course, I mean, it would probably be interesting also to consider the deformations of the brackets that you've constructed on those projective bundles.
Yeah, but yeah, unfortunately, right now the two projects are kind of like have their own life, like they need different methods. So for this project, I just do co-Higgs fields and study co-Higgs fields without using L-infinity brackets.
Thank you.
Maybe just a general question. I mean, I understand you get the classification in terms of local normal forms and so on, but do you also get, so to speak, concrete examples? Means things that one can easily write down in coordinates and things like that?
Yeah. In each case, you can produce these examples, many of these examples. But like so for instance, the example that would be easy to discuss would be, like in resonant case, consider so this is a global picture for the global example. And here the spectral curve is like this. So it has 1, 0 section and then elliptic curve, which I draw. It looks disconnected here, but over complex numbers, it's connected elliptic curve. So there are 4 points of singularities, where with singularities, the simplest one, A1. And what the Poisson structure, first of all, I can write down the expression for this in coordinates, but the picture looks like this. So the elliptic curve lives in some plane, and then the 0 set of the Poisson structure. And then there is also a component corresponding to the 0 part of the spectral curve, this spectral curve. And then that curve, so eigenvectors with 0 eigenvalues, they do not form 0 set of the Poisson structure. So the Poisson structure does not vanish there, but it does vanish on this elliptic curve. And here in this picture, you have all this behavior that I was talking about in the local example. So each fiber here, which I didn't draw in this case, but each fiber here kind of has all these quadrics, family of quadrics that are integral curves of the co-Higgs field. And they have 4 degenerations around 4 of these singular points. And these 4 special fibers, they have also family of quadrics, but they're gonna look a little bit differently from the general type. So you have this local picture 4 times here in this global example. So that's what kind of Poisson structure you can obtain in this case. So I guess also Brent was asking question in the chat, does this correspond to the 0 locus of the Poisson structure being, sorry, that was question about the previous case. But the comment about Brent's question is that it's not always true that the kind of counterpart of the spectral curve in the projective bundle, it's not always the set of zeros of Poisson structures. It may or may not be the set of zeros of Poisson structure. So you can prove that this set of 0 of the Poisson structure is contained in this, but it's not always equal to. So here in this case, Poisson structure vanishes on the elliptic curve, but it does not vanish on this line, on this section of the P1 bundle.
Okay, yeah, any further questions? Well, if that's not the case, then let's thank Mykola once again for a nice talk.
Thank you for all the questions.
And see you again next week.
Bye-bye.